Beneath the perpetual hush of glacial wind, mountains hold secrets older than memory itself. They are not merely geological formations but vertical archives of Earth's most turbulent autobiography, compressed millennia made visible, silence made structural. To stand at the base of a great peak is to confront something profoundly humbling, a scale of time so vast that human civilization occupies less than a breath within it. The mountains were here before language gave them names, before myth assigned them gods, before science dared measure their silhouettes against the sky. This documentary is an invitation, not to conquer these towering witnesses, but to listen to what they have always been quietly declaring to those willing to ascend slowly enough, reverently enough, to truly hear. The Himalayan range, that extraordinary spine of the Asian continent, did not rise through any single cataclysmic event but rather through a prolonged, almost meditative collision that began approximately 50 million years ago. When the Indian subcontinent, itself a vast geological wanderer that had broken free from the ancient supercontinent Gondwana, drifted inexorably northward at roughly 5 centimeters per year, it eventually met the Eurasian plate with a force that defies ordinary comprehension. The oceanic crust between them, being denser than continental rock, subducted downward into the mantle, vanishing into Earth's interior like a slowly swallowed document. What remained was the crumpling and uplift of continental material, layer folding upon layer in geological origami of breathtaking complexity. That process has never fully ceased. The Himalayas continue rising by approximately 5 millimeters each year, though erosion simultaneously carves them down, creating a dynamic equilibrium that makes these peaks eternal works in progress rather than finished monuments. Mount Everest, known in Tibetan as Komolungma, goddess mother of the world, and in Nepali as Sagarmatha, forehead of the sky, does not hold its position as Earth's highest point above sea level without geological intrigue. Its summit, composed largely of marine limestone, contains fossilized sea creatures, ancient shells, coral fragments, and the calcified remains of organisms that once drifted through warm Tethys sea waters roughly 470 million years ago. This astonishing fact means that the highest point on Earth is, in a profound sense, an ocean floor elevated to the boundary between atmosphere and space. When climbers touch the summit pyramid, they touch what was once submerged beneath a shallow tropical sea, a reminder that geology operates on timescales that render human intuitions about permanence almost comically inadequate. Recent GPS surveys have revised Everest's official height to 8,848.86 meters, acknowledging that even our measurements must be renegotiated with a living, breathing planet. Tectonic plates, those vast and ponderous slabs of lithosphere upon which continents drift like islands on a slow river, are driven by convective currents deep within Earth's mantle. Heat generated by radioactive decay causes mantle material to circulate in enormous loops, hot rock rising, spreading laterally, cooling, sinking, creating a conveyor belt mechanism that drags the overlying plates in its wake. When two plates carrying continental material converge, neither can easily subduct because both are composed of relatively buoyant rock. The result is a collision zone, material compressed, folded, thickened, and ultimately forced skyward. This is the engine behind virtually every great mountain range on Earth. The Alps formed when the African plate pushed against Eurasia. The Andes arose where the Nazca Oceanic plate dove beneath South America. The Appalachians record an even older collision, now worn smooth by hundreds of millions of years of erosion, a ghost range whispering of its former Himalayan grandeur through rounded ridges and soft, rain-darkened slopes. Granite, that crystalline and speckled rock so characteristic of mountain cores, tells an extraordinary story about heat, pressure, and geological patience. It forms deep beneath the surface when magma intrudes into existing rock and cools slowly over millions of years, allowing crystals of quartz, feldspar, and mica to grow to visible size. The mountain building process subsequently forces these once buried masses upward while erosion strips away the overlying material, eventually exposing granite that crystallized kilometers underground. The walls of Yosemite Valley formed approximately 80 to 100 million years ago at depths of perhaps 15 kilometers. When you place your palm against the warm surface of a granite dome in afternoon sunlight, You are touching rock that has journeyed from the profound darkness of Earth's interior to the brightness of open sky, a passage lasting tens of millions of years, completed in geological silence. Glaciers are among the most eloquent sculptors in the natural world, and their handiwork is etched into mountain landscapes with a precision that no human artisan could replicate. When snow accumulates faster than it melts over successive centuries, it gradually compresses under its own weight into dense, crystalline ice. This ice, subjected to immense pressure, begins to flow, slowly, imperceptibly by human measure, but relentlessly across geological time. As it moves, it plucks rock fragments from the valley floor and walls, embedding them within its base like teeth in a great grinding jaw. The result is the characteristic U-shaped valley, smoothed and deepened beyond what any river could achieve. Cirques, those dramatic amphitheater-like basins carved into mountainsides where glaciers are born, arêtes, the knife-edged ridges between adjacent glacial valleys, and horns like the Matterhorn's iconic pyramid are all signatures of this frozen architecture, written in stone across every high mountain range on Earth. The color of glacial ice, that luminous, otherworldly blue that photographs scarcely capture, arises from a physical phenomenon both elegant and counterintuitive. Freshly fallen snow appears white because its complex crystalline structure scatters all wavelengths of visible light equally. But as snow compresses into glacial ice over decades and centuries, the air bubbles that once scattered light are gradually expelled. What remains is an increasingly pure and dense medium through which light must travel appreciable distances. Ice absorbs the longer, redder wavelengths of visible light more readily than the shorter, bluer wavelengths. The deeper the light penetrates before being scattered back to the observer, the more red has been absorbed, and the more intensely blue the returned light appears. Ancient glacial ice, compacted over centuries, achieves a depth of blue so saturated and pure, almost electric, almost alive, that standing before a glacier's face on a clear afternoon feels less like looking at frozen water and more like gazing into the distilled essence of coldness itself. The cryosphere, that collective term for all frozen water on Earth's surface, stores approximately 69% of the planet's fresh water, the vast majority locked in the great ice sheets of Antarctica and Greenland. But mountain glaciers, though representing a far smaller fraction of total ice volume, are of disproportionate importance to human civilization. They function as natural reservoirs, accumulating winter snowfall and releasing it gradually through summer melt, sustaining river flows during dry seasons when rain is absent. The Hindu-Kush Himalayan system alone feeds 10 of Asia's most significant river systems, providing water to nearly 2 billion people. These glaciers are sometimes called the third pole, a designation that captures both their immensity and their critical global role. As atmospheric temperatures rise and these frozen reservoirs diminish, the implications for agriculture, drinking water, hydroelectric power, and regional stability across vast portions of South and Central Asia grow increasingly difficult to overstate. Moraines, those distinctive ridges and mounds of rock debris deposited by glaciers, serve as geological diaries, recording the advance and retreat of ice over centuries. Terminal moraines mark the furthest extent a glacier reached before warming caused it to retreat. Lateral moraines accumulate along the sides of glacial tongues. Medial moraines form where two glaciers merge, their lateral moraines combining into a single dark stripe flowing down the center of the united ice. By studying moraine sequences, glaciologists can reconstruct glacial histories stretching back thousands of years, reading advances and retreats as clearly as a historian reads handwritten letters. The moraines around Mont Blanc, studied intensively since the 19th century, reveal medieval advances and subsequent retreats, connecting the behavior of ice to broader patterns of climate oscillation. In this way, the physical debris of glaciation becomes testimony, not merely geological but climatological, a frozen record of Earth's thermal biography written in boulders and gravel. Above approximately 3,500 meters in most temperate mountain ranges, the forest gives way to a landscape of diminishing stature and increasing openness known as the alpine zone. The transition is not always abrupt. It proceeds through a characteristic krummholz, that haunting German word meaning crooked wood, a zone where trees persist but in forms so distorted by wind, ice, and cold that they seem to belong to some alternative botanical mythology. Conifers that stand 30 meters tall in valley forests become sprawling, horizontal mats here, their windward branches killed back each winter while leeward growth creeps centimeters at a time along the ground. Some individual crumholes trees, measured by their girth rather than height, are centuries-old organisms of remarkable longevity reduced to near invisibility by environmental severity. Beyond the crumholes lies the true alpine meadow, where herbaceous plants, sedges, cushion plants, and low-growing shrubs replace forest entirely, and where the ecology of exposure begins its most fascinating negotiations with survival. The cushion plant growth form, that dense, hemispherical architecture adopted independently by hundreds of unrelated alpine plant species across the world's mountain ranges, represents one of evolution's most compelling examples of convergence. From the Andes to the Alps, from the Himalayas to the mountains of New Zealand, plants facing similar challenges of cold, wind, and desiccation have arrived at remarkably similar solutions. A tight, domed form that minimizes wind resistance, traps heat within its interior, reduces water loss, and presents only the upper surface of leaves to damaging ultraviolet radiation. The interior of a cushion plant can be measurably warmer than the surrounding air, sometimes by as much as 10 degrees Celsius on a sunny day. A microclimate of extraordinary significance for the insects and invertebrates that shelter within. Some cushion plants, such as certain species of azurella in the Andes, grow so slowly that individual specimens several meters across may be thousands of years old, among the most ancient living organisms in their respective ecosystems. High-altitude plants must contend with ultraviolet radiation significantly more intense than that experienced at sea level, not because they are closer to the sun in any meaningful sense, but because the thinner atmosphere above them filters out less of the sun's energetic shorter wavelengths. At 4,000 meters, UV radiation may be 25 to 50% more intense than at sea level on a clear day. Alpine plants have evolved a remarkable pharmacopoeia of protective compounds in response. Flavonoids, anthocyanins, and other UV-absorbing pigments concentrate in leaf surfaces, functioning as biological sunscreens. These compounds are also responsible for the extraordinary intensity of color in alpine flowers, the deep purples, vivid blues, and saturated yellows that seem almost unreal against the gray rock and white snow of their environment. Some alpine botanists have argued that alpine flower color is not merely an evolutionary response to UV but simultaneously an adaptation for rapid heat absorption in cold conditions, with darker pigments warming floral tissues and attracting the scarce pollinating insects at altitude. The bar-headed goose performs one of the most physiologically extraordinary migrations in the animal kingdom, crossing the Himalayan range twice annually between its breeding grounds on Central Asian plateau lakes and its wintering grounds in South Asia. These birds have been documented flying at altitudes exceeding 7,000 meters, above the summit of most mountains in the world outside the Himalayas themselves, and do so in conditions that would render most birds, and certainly most mammals, rapidly incapacitated. Their adaptation involves multiple coordinated physiological innovations. Hemoglobin with a modified alpha subunit that binds oxygen with greater affinity than most bird hemoglobin, a higher capillary density in flight muscles allowing more efficient oxygen delivery, and a respiratory system capable of extracting oxygen with exceptional efficiency at partial pressures so low they approach the limits of aerobic metabolism. Remarkably, bar-headed geese do not necessarily fly over the highest passes but rather follow topographic contours, descending and ascending with the mountain terrain rather than maintaining constant altitude, conserving energy while navigating the vertical wilderness. The snow leopard, that ghost of the Asian highlands, moves through terrain so steep, so cold, and so remote that it remained, for much of human scientific history, more legend than documented reality. Inhabiting mountain ranges from the Hindu Kush to the Russian Altai, and from the Tibetan Plateau to the ranges of Mongolia, the snow leopard has evolved over millennia into a near-perfect expression of high-altitude predatory existence. Its paws are extraordinarily large relative to body size, functioning as natural snowshoes that distribute weight across soft, unpacked snow. Its tail, sometimes as long as its body, serves multiple functions. a balancing organ during the acrobatic leaps required to navigate near vertical terrain, a thermal wrap coiled around the face during rest in sub-zero temperatures, and reportedly a comfort object held in the mouth during rest. Population estimates remain uncertain, but the total wild population may number only 4,000 to 6,000 individuals, each occupying territories of hundreds of square kilometers of virtually uninhabited high-altitude wilderness. The Himalayan jumping spider, Euophrys omnisupersts, whose Latin name translates, with appropriate grandeur, as standing above everything, holds the distinction of living at higher permanent elevations than any other known animal on Earth. Specimens have been collected from the southern face of Everest at altitudes exceeding 6,700 meters, making this small arachnid a permanent resident at elevations most mountaineers find challenging even with supplemental oxygen. Its prey at such altitudes consists primarily of wind-blown insects and other arthropods carried upward on updrafts from lower elevations, a dietary strategy dependent entirely on the mountain's role as an atmospheric collector and concentrator of material from the world below. The spider's existence at these elevations challenges our intuitions about where biology ends and pure physics begins, suggesting that the boundary of habitable space is more negotiable than common sense would predict, pushed outward by evolutionary innovation at every margin of the apparently possible. High-altitude lakes, those cold and often startlingly blue or turquoise bodies of water nestled in glacial cirques and mountain valleys, exist within ecological conditions so extreme that they were long assumed to be essentially lifeless. Modern limnology has thoroughly revised this assumption. Even in lakes of the high Andes and Himalayas, beneath ice covers that may persist for most of the year, complex microbial communities thrive, photosynthetic cyanobacteria forming layered mats along lake floors, archaea processing nutrients under conditions of cold, high UV, and low organic input that would seem to preclude biological activity. Some of these high-altitude lakes are extraordinarily clear, their transparency a product of extremely low nutrient inputs, oligotrophic conditions that support minimal biological productivity. Yet in this clarity they function as unique sensors of atmospheric deposition. Their sediments accumulate particulate material falling from the atmosphere above, including pollutants from distant industrial sources, making them inadvertent monitors of global atmospheric chemistry. The treeline, that ecological boundary above which continuous forest cannot persist, is not a fixed altitude but a dynamic threshold shaped by temperature, wind, snow, soil conditions, and the specific physiological tolerances of the tree species involved. In the Alps, treeline typically occurs around 2,000 meters. In the tropical Andes near the equator, it may reach 3,500 meters or higher. In subarctic ranges, it may descend to near sea level. The underlying physiological constraint is primarily thermal. Tree growth requires a mean temperature during the growing season of at least approximately 6 to 7 degrees Celsius, a threshold that defines where woody tissue can form fast enough to sustain upright growth. Climate warming is causing treelines in many ranges to migrate upward, a process measurable over decades of systematic observation. This treeline advance is not without ecological consequence. The specialized alpine communities above are being compressed, their habitat slowly colonized from below by advancing forest, a creeping transformation that is both biologically fascinating and potentially catastrophic for the specialized organisms of the high alpine zone. Precipitation patterns in mountainous terrain are shaped by a phenomenon of elegant physical logic, the orographic effect. When moisture-laden air masses moving horizontally encounter a mountain barrier, they are forced upward. As air rises, it expands and cools adiabatically, that is, without exchanging heat with its surroundings, at a rate of approximately 10 degrees Celsius per 1,000 meters of ascent. Cooling reduces the air's capacity to hold water vapor, eventually reaching saturation and triggering condensation and precipitation. The windward slopes of mountain ranges therefore tend to be dramatically wetter than the surrounding lowlands. The leeward side, the so-called rain shadow, receives air that has surrendered its moisture on the windward ascent and now descends, warming and drying as it does. This simple physical mechanism is responsible for some of the world's most dramatic ecological contrasts. The rainforests of the Olympic Peninsula's windward slopes exist within a few dozen kilometers of near-desert conditions in the rain shadow of the same range. The wettest slopes of the Hawaiian mountains receive among the highest annual precipitations on Earth, while their leeward sides remain semi-arid. The jet stream, those narrow, fast-moving rivers of air at high altitudes in the atmosphere, interacts with the world's great mountain ranges in ways that shape weather patterns across entire continents. The Himalayan and Tibetan Plateau Massif in particular exerts profound influence on the global atmospheric circulation, helping to establish and maintain the monsoon systems upon which much of Asian agriculture depends. In winter, the jet stream splits to flow both north and south of the Tibetan Plateau, helping to drive cold Central Asian air masses southward. In summer, the intense heating of the plateau's surface drives convection that helps pull the monsoon circulation northward, bringing seasonal rains to South Asia. Mountain ranges elsewhere create their own atmospheric influences. The Rockies generate stationary planetary waves in the jet stream that influence weather patterns across North America and the North Atlantic. The mountains are, in this sense, not merely passive features of the landscape but active participants in the planet's atmospheric machinery. At the summit of the world's highest peaks, the atmosphere becomes something qualitatively different from what sustains life in the valleys below. At 8,000 meters, the altitude that climbers call the death zone, the atmospheric pressure is approximately 1/3 of sea level pressure, meaning that each breath delivers proportionally less oxygen to waiting lung tissue. The partial pressure of oxygen, which drives its diffusion from air into blood, falls to levels at which the human body's oxygen delivery systems are overwhelmed. Acclimatization, the physiological process by which the body adjusts to altitude, can mitigate but not eliminate this deficit. The kidneys excrete bicarbonate to compensate for respiratory alkalosis caused by hyperventilation. The bone marrow produces additional red blood cells to carry more oxygen per unit of blood volume. The heart rate elevates, and certain metabolic pathways become more efficient. Yet above approximately 8,000 meters, even fully acclimatized climbers deteriorate rather than adapt, their bodies in slow physiological decline every hour they remain at such altitude. The summit of Mauna Kea in Hawaii, measured from its oceanic base on the floor of the Pacific, stands approximately 10,210 meters tall, significantly exceeding Everest's 8,848.86 meters of elevation above sea level. This distinction matters because it reminds us that the concept of highest mountain depends entirely on what reference point we choose. If we measure from Earth's center rather than sea level, Mount Chimborazo in Ecuador, located near the equatorial bulge of the slightly oblate Earth, extends further from the planetary center than Everest. If we measure total height from base to summit, Mauna Kea claims the title. If we measure the length of the mountain's actual slopes, certain Antarctic peaks may rival anything in the Himalayas. These geometrical nuances are not merely academic curiosities. They reveal how profoundly our perception of natural superlatives is shaped by the particular frameworks through which we choose to measure, a lesson extending well beyond cartography. The atmospheric phenomenon known as a lenticular cloud, those smooth, lens-shaped formations that hover above mountain peaks with an eerie, almost artificial precision, forms when stable, moist air is deflected upward over a mountain barrier and sets into oscillating waves on the downwind side. As air rises in the wave crests, it cools and moisture condenses. As it descends in the troughs, air warms and cloud droplets evaporate. The result is a standing wave in the atmosphere, and the cloud that marks the crest of each wave appears stationary even as the air flowing through it is moving rapidly. Lenticular clouds have been mistaken for unidentified flying objects in scores of historical reports. Their geometric smoothness, their apparent motionlessness while surrounding clouds drift, their sudden appearance and disappearance all conspiring to confuse observers unfamiliar with the physics involved. Mountain communities throughout history developed their own interpretations. In many traditions, the cloud hovering above the sacred peak was understood as evidence of divine presence, the mountain breathing or communicating. The fen wind, that warm, dry, gusty wind that descends the leeward slopes of alpine ranges, has fascinated and unsettled European mountain communities for centuries. When maritime air crosses the Alps from the south, it rises and deposits precipitation on the Italian side, then descends on the Austrian and Swiss side as dramatically warmer, drier air. The warming occurs because descending air compresses and heats at the dry adiabatic lapse rate, roughly 10 degrees Celsius per 1,000 meters, while having surrendered moisture and its associated latent heat during the ascent. The result can be a temperature rise of 10 to 20 degrees Celsius within hours on the north side of the Alps. Villages report spectacular snow melt, orchard blossoms appearing days earlier than expected, and a peculiar psychological restlessness that local tradition attributed to the wind itself. Alpine folklore is saturated with references to the fen's disruptive influence on mood and cognition, a perception that some modern researchers have cautiously investigated, finding correlations between fen conditions and reports of headache, irritability, and disturbed sleep in susceptible individuals. The first documented attempt to measure mountain height using scientific instrumentation belongs to European natural philosophers of the 18th century, who applied the principles of trigonometry and barometric pressure measurement to peaks that had previously been estimated only by intuition and awe. The measurement of Mont Blanc's height became something of an obsession for Geneva-based naturalist Horace Benedict de Saussure, who not only contributed to its precise measurement but led the third ascent of the mountain in 1787. His Voyages dans les Alpes represents one of the foundational texts of mountain science, a work in which systematic observation, philosophical reflection, and aesthetic rapture coexist in a manner characteristic of Enlightenment natural philosophy at its best. De Saussure's instruments, barometers, thermometers, anemometers, hygrometers, accompanied him to altitudes where no scientist had previously ventured, and his readings established the empirical foundation upon which modern alpine meteorology and glaciology would eventually be constructed. The first ascent of Mont Blanc on August 8, 1786, by crystal hunter Jacques Balmat and physician Michel Gabriel Paccard, is conventionally regarded as the birth of alpinism, the pursuit of mountain summits as an end in itself rather than a means of crossing from one valley to another. This distinction matters enormously in cultural history. Prior to Balmat and Paccard's ascent, European mountaineers were primarily guides, hunters, mineral prospectors, or military surveyors with instrumental reasons to venture upward. The deliberate ascent of a high peak for the experience of reaching its summit represented a conceptual revolution, an expression of Romantic-era values that held the sublime, the extreme, and the personally transformative in the highest aesthetic regard. Mont Blanc's first ascent inaugurated a tradition of mountain exploration that would, within a century, send expeditions to every inhabited and uninhabited range on Earth, culminating in the 20th century assault on the 8,000ers of the Himalaya. The golden age of alpine mountaineering, spanning roughly from 1854 to 1865, witnessed the first ascent of nearly every major peak in the Alps by British climbers guided by local Swiss, French, and Italian mountain men whose knowledge of the terrain was encyclopedic and whose physical capabilities were extraordinary. Edward Whymper's ascent of the Matterhorn on July 14, 1865, is the most famous achievement and most famous tragedy of this era, for members of his summit party fell to their deaths on the descent, and the disaster sparked a public debate in Britain about the morality of risking life for the vanity of mountain summits. Queen Victoria herself reportedly considered legislation to prohibit mountaineering. Yet the deaths on the Matterhorn did not diminish the sport. Paradoxically, the tragedy amplified public fascination with the mountains, lending alpinism an aura of heroic transgression and existential seriousness that transformed it from athletic hobby into cultural phenomenon. The thin air of extreme altitude affects not only the body but the mind in ways that mountaineers have described with haunting consistency across more than a century of high-altitude literature. At 8,000 meters and above, cognitive impairment is not merely possible but essentially universal. Decision-making slows, judgment becomes unreliable, hallucinations occur, and the fundamental will to survive can paradoxically diminish. Hermann Buell, who made the first ascent of Nanga Parbat in 1953 alone and without oxygen, later described his descent as occurring in a semi-hallucinatory state in which he conversed with an invisible companion. Reinhold Messner, after his oxygen-free solo ascent of Everest in 1980, wrote of perceiving a second presence on the summit. These experiences, now known from neurological research to reflect the brain's response to hypoxia, combined with extreme fatigue and isolation, have been interpreted by climbers themselves as encounters with something beyond the ordinary world, endowing extreme altitude mountaineering with a mystical dimension that purely physiological explanation cannot entirely dissolve. George Mallory's 3 Everest expeditions, 1921, 1922, and 1924, occupy a singular place in mountaineering history, partly because of their physical courage and partly because of the unanswered question they bequeathed to posterity. Mallory and his climbing partner Andrew Irvine were last seen on June 8, 1924, moving upward through a break in the clouds near the summit pyramid, going strong, according to the witness Noel Odell. They never returned. The discovery of Mallory's body in 1999 at approximately 8,155 meters provided new evidence but could not resolve the central mystery. Did Mallory and Irvine reach the summit 29 years before Hillary and Tenzing? The Kodak camera Irvine was known to carry was not found with Mallory's body. Were its film ever recovered and successfully developed, it might answer a question that has animated mountaineering debate for a century. That ambiguity, that suspended, unresolved moment high in the death zone, has given Mallory's story the quality of myth. The hero who may have achieved the impossible and vanished, leaving only the mountain's silence as testimony. Tenzing Norgay and Edmund Hillary reached the summit of Mount Everest at 11:30 a.m. on May 29, 1953, an achievement that resonated globally as a triumph both of human capability and of careful, systematically organized expedition mountaineering. What is less universally appreciated is the degree to which the success depended on the accumulated knowledge and physical labor of the Sherpa people, whose high-altitude physiological adaptations, intimate familiarity with Himalayan terrain, and extraordinary endurance were indispensable to virtually every Himalayan expedition of the 20th century. Tenzing Norgay was not merely an assistant to Hillary but an experienced high-altitude climber who had attempted Everest multiple times and whose judgment and physical performance were in every way equal to his climbing partners. The framing of the ascent in much subsequent Western reporting, Hillary as protagonist, Tenzing as supporting figure, reflects cultural assumptions about whose achievements deserve centered narration, assumptions that the history of Himalayan mountaineering is slowly, if belatedly, revising. The 8,000ers, those 14 peaks whose summits exceed 8,000 meters above sea level, represent the extreme margin of the high-altitude world, and their full list constitutes something like a sacred geography of the vertical: Everest, K2, Kanchenjunga, Lhotse, Makalu, Cho Oyu, Dhaulagiri, Manaslu, Nanga Parbat, Annapurna, Gusherbrum I, Broad Peak, Gusherbrum II, and Shishapangma. All are located in the Himalayan and Karakoram ranges of Asia. K2, the second highest, is widely considered the most technically demanding and dangerous, with a fatality rate significantly exceeding Everest's. Annapurna, at 8,091 meters, historically holds the highest ratio of deaths to summit attempts of any 8,000er. Reinhold Messner completed the first ascent of all 14 without supplemental oxygen between 1970 and 1986, a feat of endurance, technical skill, and systematic ambition that remains one of the defining achievements in the history of human exploration of extreme environments. The Sherpa people of Nepal's Khumbu region, the high valleys below Everest and its neighbors, are among the most physiologically adapted human populations to high-altitude existence on Earth. Research has identified multiple genetic variants in Sherpa populations that distinguish them from lowland Tibetan and Han Chinese populations, variants affecting hemoglobin regulation, mitochondrial function, and vascular response to hypoxia. Particularly significant is a variant in the EPAS1 gene, the superathlete gene, associated with regulation of the body's response to oxygen deprivation, that appears to have been introduced into the Sherpa gene pool through ancient interbreeding with Denisovans, a now extinct archaic human population known primarily from fragmentary fossil evidence. This remarkable finding connects Himalayan physiological adaptation to a lineage of human evolution stretching back hundreds of thousands of years, suggesting that the high mountains shaped not only the landscape but the very genetic architecture of the people who have called them home across countless generations. The Great Surveys of the Himalaya conducted by the British during the 19th century represent one of history's most ambitious scientific projects. The Great Trigonometrical Survey of India, initiated in 1802 and continuing for decades, extended its measurement framework northward from peninsular India toward the Himalayan ranges, employing enormous theodolites, painstaking triangulation, and the labor of thousands of surveyors operating in terrain of extreme difficulty and climatic severity. It was through this survey that Peak 15, the designation of the highest mountain then known only by its surveyed coordinates, was calculated in 1856 to be the world's tallest peak. The mountain was subsequently named Everest in honor of Sir George Everest, the Welsh surveyor who directed much of the Great Survey's work, though Everest himself had reservations about the honor and noted that local peoples had perfectly serviceable names for the peak already. The survey's legacy is complex, a monument to scientific precision achieved through colonial infrastructure, producing knowledge that served both genuine cartographic purpose and the imperial project it accompanied. The discovery of a young girl's mummified body near the summit of Uyayaka, a 6,739-meter volcano on the Argentine-Chilean border, in 1999 opened a window into Inca capicocha ritual that no historical document had previously provided with such intimate immediacy. The Maiden of Uyayaka, estimated to have been between 13 and 15 years of age at death, was found accompanied by miniature gold and silver figurines, fine textiles, and other ceremonial objects, in a state of preservation so remarkable, a consequence of the peak's dry, perpetually frozen conditions, that her facial features remain distinct and her internal organs intact. Isotopic analysis of her hair revealed changes in diet and consumption patterns in the months before her death consistent with a journey from her home community to Cusco and then to the summit, a process understood within Inca cosmology as elevation to divine status rather than execution. The mountain had received her not as a place of death but, within the system of belief that sent her upward, as a threshold between the human and the sacred. The mountains of the Greek world, Olympus, Parnassus, Helicon, Ida, occupied a central position in Greek religious geography, functioning simultaneously as physical barriers, meteorological generators, and mythological domiciles. Mount Olympus, at 2,917 meters, the highest peak in Greece, was understood as the residence of the Olympian gods not in a merely symbolic sense but as their actual, physical home. Homer's descriptions of Olympus include references to its cloud-covered summit, the brilliant light above the clouds, and the activities of divine beings on its heights that reflect genuine observations of high alpine weather translated into mythological narrative. The tradition of mountain divinity in Greek culture drew on older, pre-Hellenic religious sensibilities connecting peaks with storm gods and sky deities, sensibilities that were not unique to Greece but appear across Mediterranean, Near Eastern, and Indo-European cultures, suggesting a near-universal human intuition that power, proximity to sky, and altitude are conceptually linked. In Japanese tradition, Mount Fuji, Fujisan, is not merely Japan's highest peak but its most sacred mountain, the object of a pilgrimage tradition stretching back at least 12 centuries and the spiritual focus of a Shinto and Buddhist devotional culture of extraordinary richness. The mountain is considered a feminine deity, associated with the goddess Kano Hanasakyaheim, whose domain includes fire, flowering trees, and the ephemerality of beauty, symbolism that connects Fuji's volcanic origin, its snow-covered symmetry, and its association with cherry blossom season into a coherent mythological unity. The Fujiko, religious confraternities devoted to Fuji pilgrimage, organized group ascents for centuries, treating the climb as a form of purification and spiritual transformation rather than athletic achievement. The mountain's near-perfect conical symmetry, visible on clear days from Tokyo and widely represented in Japanese visual culture, has made it a national symbol with a cultural resonance exceeding that of virtually any natural feature in any other country, a mountain that functions simultaneously as landscape, deity, and national identity. The sacred mountain in many indigenous traditions of the Americas is understood not as a static geological feature but as a living, intentional being, a person of immense age and power with whom human communities maintain ongoing reciprocal relationships. The Lakota people's relationship with the Black Hills, Pahasapa, the heart of everything that is, involves a cosmological connection to the hills as birthplace and ancestral home that transcends the categories of either property or ecology as those terms function in Western legal and scientific discourse. The Navajo Sacred Mountains, Blanca Peak, Mount Taylor, the San Francisco Peaks, and Hesperus Peak, mark the four corners of the Navajo homeland and are understood as living bodies whose maintenance and protection are inseparable from the maintenance and protection of Navajo cultural continuity. The ongoing disputes between these traditions and extractive industries, recreational developers, and government entities over access to and development of sacred peaks represent some of the most complex intersections of cultural, legal, and ecological values in contemporary land use debates. The Alps gave rise not only to alpinism as a sporting practice but to a distinctive literary and philosophical tradition that transformed European attitudes toward mountain landscape. Before the late 18th century, mountains were widely regarded in European culture as frightful, chaotic, and aesthetically repugnant, the antithesis of the ordered, productive landscape that educated sensibility admired. Rousseau's writings about his walks in the Alpine foothills, Schiller's dramatic evocations of Swiss mountain freedom, Goethe's ascents in the Harz Mountains, and ultimately the Romantic poet's passionate engagement with Alpine sublimity, Shelley's Mont Blanc, Byron's Manfred, Coleridge's Alpine musings, collectively inverted the prevailing aesthetic, making mountain wilderness not merely tolerable but actively desirable as a site of spiritual renewal, philosophical reflection, and emotional authenticity. The Alps became the landscape of romantic inwardness projected outward, places where the confrontation with geological immensity catalyzed the confrontation with psychological depth, where the external sublime and the internal sublime became mirrors of each other. John Muir, the Scottish-born naturalist who became the founding prophet of American wilderness conservation, developed his philosophy of natural sanctity in large part through intense engagement with the Sierra Nevada, a mountain range he explored with a combination of scientific rigor and unashamed mystical rapture. Muir's mountains were, for him, cathedrals rather than challenges, places whose value lay not in the summiting of their peaks but in the contemplative immersion in their landscapes, their glaciers, their forests, their storms. His writings on the Sierra, particularly the mountains of California and My First Summer in the Sierra, articulate a theology of wildness in which the mountain ecosystem is understood as both the expression and the dwelling place of divine creative intelligence. Muir's advocacy led directly to the establishment of Yosemite National Park in 1890 and eventually to the founding of the Sierra Club, making his alpine philosophy one of the most consequential environmental ideas in American history, with reverberations extending through a century of conservation legislation and still unresolved debates about the relationship between human civilization and wild land. The Bernese Oberland of Switzerland, that region of the Central Alps whose north face presents a dramatic escarpment of ice-draped limestone walls, the Eiger, Mönch, and Jungfrau, produced, in the 19th and early 20th centuries, a concentration of mountaineering innovation, tragedy, and legend unparalleled in alpine history. The north face of the Eiger, the Nordwand, known with grim affection among climbers as the Mordwand or Murder Wall, is a 1,800-meter sweep of rock, ice, and debris so frequently swept by rockfall and storm that its first ascent in 1938 by a German-Austrian team required 4 days of desperate survival climbing under conditions of extreme meteorological violence. More than 60 climbers have died on the Nordwand since then. The face has attracted the attention of the finest technical climbers of each generation not merely as an athletic challenge but as an existential arena in which the human will to persist against apparently overwhelming natural force is tested with a completeness impossible to simulate in safer environments. The concept of acclimatization, the body's gradual physiological adjustment to reduced oxygen availability at altitude, was poorly understood by the first generation of Himalayan climbers, with occasionally fatal consequences. It is now known that a minimum of 2 to 3 weeks at intermediate altitudes, typically between 3,000 and 5,500 meters, is required before the body has made sufficient physiological adjustments to safely attempt extreme altitudes. The climb high, sleep low protocol, ascending to greater altitude during the day before descending to sleep at a lower camp, accelerates acclimatization by stimulating red blood cell production and other adaptive responses without exposing the climber to the deteriorative effects of prolonged extreme altitude exposure. Above approximately 5,500 meters, complete acclimatization becomes physiologically impossible. The body adapts to tolerate, but cannot fully accommodate, the conditions of the high Himalaya. Even experienced, fully acclimatized climbers sustain measurable cognitive and physiological deficits during extended periods above 7,000 meters that require weeks or months at low altitude to reverse. The mountain medicine field born from high-altitude physiology has contributed insights extending far beyond mountaineering into clinical cardiology, pulmonology, and the treatment of conditions ranging from congenital heart disease to chronic obstructive pulmonary disease. The study of how the body responds to hypoxia, oxygen deficiency, at altitude illuminated the mechanisms of oxygen transport and utilization in ways that bench research could not easily replicate. Understanding how EPO, erythropoietin, production increases at altitude in response to low oxygen partial pressure led directly to the development of synthetic EPO as a treatment for anemia in cancer patients and those with kidney failure, and, notoriously, to its misuse as a blood doping agent in competitive cycling and other endurance sports. The molecular mechanisms of HIF-1-alpha, the transcription factor that orchestrates the cellular response to hypoxia, were worked out partly through altitude research and have since become central to cancer biology, wound healing, and the understanding of how tumors exploit hypoxic conditions within solid tissue masses. The Tibetan Plateau, sometimes called the roof of the world, covers approximately 2.5 million square kilometers at a mean elevation of over 4,500 meters above sea level, making it the world's largest and highest plateau and one of the most geographically distinctive regions on Earth. It formed as the accumulated result of the same India-Eurasia collision that built the Himalayas, with crustal material thickening and rising over tens of millions of years. The plateau's immense elevation affects atmospheric circulation at a global scale. Its summer heating drives the South Asian monsoon, its winter cooling influences jet stream positioning, and its existence as a massive elevated heat source fundamentally distinguishes Asian atmospheric patterns from what they would be in its absence. The plateau is also the source of Asia's 10 major river systems: the Yangtze, Yellow, Mekong, Salween, Irrawaddy, Brahmaputra, Indus, Sutlej, Karnali, and Arun, whose combined watershed sustains roughly half of humanity, making the Tibetan Plateau perhaps the most consequential hydrological feature on Earth's surface. The unique ecology of the Tibetan Plateau, its vast expanses of cold steppe, its alkaline lakes, its wind-scoured plains and river valleys, supports a remarkable assemblage of large mammals that have adapted over long evolutionary history to conditions of cold, aridity, and altitude that would challenge most large-bodied animals. The Tibetan antelope, or kairu, undergoes one of the great ungulate migrations on Earth, with tens of thousands of pregnant females converging annually on remote calving grounds in the northern plateau, moving hundreds of kilometers through terrain of extraordinary harshness. The wild yak, ancestor of the domesticated yak upon which Tibetan pastoral culture is built, possesses physiological adaptations to cold and altitude, including remarkably dense underfur, a reduced number of sweat glands, and a modified hemoglobin that binds oxygen more efficiently at low partial pressures. The Tibetan wolf, the snow leopard, and the rare Pallas's cat complete a predator guild that has evolved in concert with the plateau's prey base, a community forged by millions of years of coevolution in one of Earth's most demanding environments. Rock weathering in mountain environments occurs through mechanisms both chemical and physical, operating at different rates depending on temperature, moisture, rock composition, and biological activity. Physical weathering, also called mechanical weathering, is particularly prominent at high altitudes, where the daily freezing and thawing of water in rock fractures exerts extraordinary hydraulic pressure. Water, that unusual substance that expands upon freezing, exploits existing cracks, enlarging them incrementally with each freeze-thaw cycle until entire slabs of rock split free. This process, known as frost wedging or cryofracturing, produces the angular talus slopes and scree fields so characteristic of alpine landscapes, raw, recently liberated fragments of mountains still sharp-edged because they have not yet been rounded by water transport. The rates of frost weathering depend on the frequency of freeze-thaw cycles rather than the absolute depth of cold, meaning that mountain zones with many daily cycles around the freezing point weather faster than zones that remain frozen throughout winter and thaw only briefly in summer. The formation of hanging valleys, those tributary valleys whose floors sit elevated above the main valley floor, often ending in waterfalls, is among the most visually striking legacies of differential glacial erosion. When a large glacier occupies a main valley and smaller tributary glaciers join it from the sides, the main glacier erodes its floor much more deeply than the tributaries, because glacial erosion scales with ice thickness and the larger ice mass has enormously greater erosive power. When the glaciers finally retreat, the tributaries are left hanging above the deepened main valley, their floors suspended in space, their streams cascading from their elevated thresholds to the valley floor below. Yosemite Valley's extraordinary waterfalls, Yosemite Falls, Bridal Veil Fall, Nevada Fall, are all products of this differential erosion, each one marking a hanging tributary valley whose floor the main Yosemite Glacier carved away. The relationship between ice thickness, erosive power, and topographic legacy encodes the entire glacial history of a landscape in its waterfall geography. The wind at high altitude is not merely cold and fast. It is a sculptor, an architect, and an agent of biological dispersal operating at scales from the microscopic to the continental. Wind erosion at alpine elevations creates ventifacts, rocks shaped by the abrasive action of wind-driven sand and ice crystals into smooth, faceted forms with surfaces polished to a soft gloss. Wind deflation, the removal of fine particles by wind, strips soils from exposed ridges and deposits them downwind in sheltered locations, creating patterned ground, stripes and polygons of coarser and finer material arranged with almost geometric regularity across flat alpine surfaces, the visible expression of frost sorting and wind deposition working in concert. And wind transport carries biological material, fungal spores, pollen, bacteria, small insects, across mountain barriers and between isolated ecological communities, connecting what might otherwise be genetically isolated populations and seeding new arrivals in disturbed habitats that wind and ice have made available. The vertical zonation of mountain vegetation, that distinctive stacking of ecological communities from valley floor to summit, each adapted to its particular elevation band, has long provided biologists with a natural laboratory for studying the relationships between climate, species distribution, and evolutionary adaptation. Alexander von Humboldt recognized this zonation as one of the fundamental organizing principles of biogeography during his early 19th century explorations of the Andes, producing his famous Naderschmalt, a cross-sectional diagram of Chimborazo's vegetation zones that is widely recognized as one of the founding documents of ecological science. Humboldt's insight was that altitude compresses the climatic and biological gradient that latitude spreads across thousands of kilometers into a vertical column of a few thousand meters, making mountains ideal sites for comparative ecological study and demonstrating the universality of the relationship between temperature, moisture, and biological community composition across the surface of the Earth. The phenomenon of altitudinal migration, the seasonal movement of animals up and down mountain slopes in response to seasonal changes in temperature, snow cover, and food availability, creates one of the most dynamic ecological patterns in mountain environments. Elk in the Rocky Mountains spend summers grazing high alpine meadows, retreating to lower forest zones as winter deepens the snow above. Ibex in the Alps follow similar patterns, their sharp hooves and extraordinary sense of balance allowing them to exploit near-vertical terrain inaccessible to most predators. Many bird species that breed in alpine zones move downslope or depart entirely for the winter, while certain year-round residents, ptarmigan, snow buntings, white-tailed ptarmigan, remain on high ground through the most severe conditions, surviving on buried vegetation uncovered by windscour, their plumage shifting from summer brown to winter white in a camouflage transformation that tracks the seasonal presence of snow with exquisite precision, each molting triggered by photoperiod changes. Rather than by temperature, ensuring the transition occurs in advance of environmental conditions rather than merely in response to them. The lammergeier, or bearded vulture, Gypaetus barbatus, occupies a unique ecological niche in mountain systems across Africa, Asia, and Europe, having evolved the capacity to feed almost exclusively on bone. While other vultures consume flesh, the lammergeier specializes in the calcium-rich marrow within large ungulate bones, acquiring them through a behavior of remarkable ingenuity. It carries bones to height and drops them onto specific rocky surfaces called ossuaries, repeatedly striking the same stones until the bones shatter to expose the nutritious marrow within. Individual birds learn the locations of productive ossuaries and use them across their lifetimes. Young birds learn drop sites by observing adults. The lammergeier's digestive system is adapted to handle and dissolve substantial bone fragments, with stomach acid so concentrated it can dissolve an entire lamb vertebra within 24 hours. This specialization insulates the bird from competition with other large scavengers and gives it access to a food resource, the skeletal remains of mountain ungulates, that sustains it through the seasons when carcasses are most scarce. The pika, that small, round-eared relative of rabbits and hares that inhabits talus slopes across mountain ranges of North America and Asia, has become an emblematic indicator species for climate change research in mountain ecosystems. Unlike many mountain mammals, pikas do not hibernate. They remain active through winter beneath the insulating snowpack, surviving on hay piles of dried vegetation they laboriously collect and cache during summer months. This haymaking behavior is one of ecology's most celebrated examples of anticipatory food storage in a non-hibernating mammal. Because pikas are physiologically sensitive to high temperatures and cannot tolerate body temperatures much above 26 degrees Celsius for extended periods without risk of heat stress, their distribution on mountain slopes is bounded on the downslope side by thermal tolerance. As mountain temperatures warm, the suitable thermal habitat for pikas shifts upslope. On mountains of insufficient height, populations that have retreated to near summit zones have no further upward retreat available and may face local extinction, a phenomenon already documented in the Great Basin ranges of the western United States. The mycorrhizal networks connecting plant roots to fungal partners in alpine soils represent one of ecology's most significant discoveries of recent decades, demonstrating that what appears to be a collection of individual plants is in fact a community deeply interconnected through underground fungal architecture. In exchange for carbohydrates produced by photosynthesis, mycorrhizal fungi extend their hyphal networks far beyond the reach of plant roots, vastly expanding the effective nutrient foraging volume available to the plant. In alpine environments, where soils are thin, poorly developed, and often nutrient-poor, these fungal partnerships are particularly critical. Plants without mycorrhizal association are frequently unable to establish or persist in high-altitude soils. Some mycorrhizal networks connect multiple plant species, and evidence suggests that carbon and nutrients can move between connected plants through the fungal network, a form of physiological integration between organisms that challenges conventional boundaries between individual and community in ways that alpine ecologists are still working to fully understand. The spectacular wildflower meadows of the high alpine zone, the kaleidoscopic assemblages of gentians, primulas, anemones, saxifrages, and dozens of other species that carpet mountain slopes for the brief weeks of summer bloom, represent evolutionary solutions to the problem of compressing an entire reproductive cycle into the narrow thermal window available between snowmelt and first frost. Some alpine plants begin their development beneath the snow itself, utilizing solar radiation transmitted through translucent snow to initiate cell division and early leaf growth before the snowpack has fully melted. Many alpine flowers produce warming-adapted mechanisms. The bowl shape of many alpine flowers focuses solar radiation onto their reproductive organs, elevating temperatures within the floral cavity by several degrees relative to ambient air and creating warmer conditions for the development of pollen and ovules, as well as attracting the heat-seeking insects, primarily flies and small bees, that serve as their pollinators in these cold, insect-sparse environments. The extraordinary diversity of rock types exposed in mountain ranges, a geological anthology assembled by subduction, collision, metamorphism, and intrusion over billions of years, produces a corresponding diversity of soil types and mineral availabilities that shapes plant community composition across mountain slopes in patterns sometimes visible from a distance. Serpentine soils, derived from the weathering of ultramafic rocks rich in magnesium and nickel, are hostile to most plant species due to their unusual mineral chemistry, supporting instead sparse communities of specialized serpentine endemics, plants found nowhere else on Earth, adapted to chemical conditions that exclude all competition. Limestone-derived soils, alkaline and often thin but rich in calcium, support characteristic calcicolous flora distinct from that of acidic, silicate-derived soils on the same mountain. These edaphic contrasts, soil-related differences in community composition, create the fine-scale patchwork of microhabitats that contributes to the remarkable biodiversity of mountain ranges, their elevated species richness per unit area exceeding that of most lowland landscapes of equivalent extent. The relationship between mountain topography and biodiversity is one of the most actively studied questions in macroecology. Mountain ranges are consistently observed to harbor disproportionately high numbers of species relative to their area, particularly in tropical and subtropical latitudes. Multiple mechanisms contribute to this mountain biodiversity premium. Elevational heterogeneity, the range of climatic and ecological conditions packed into the vertical dimension, creates numerous distinct habitats, each supporting different species assemblages. The physical barriers between valleys and isolated high-altitude islands promote allopatric speciation, the divergence of populations isolated from gene flow by mountain ridges and impassable terrain. The geological and climatic instability of mountain regions, alternating between periods of glaciation and warming that repeatedly contracted and expanded species ranges, may have driven speciation by cyclically isolating and reconnecting populations. The result is that the great mountain ranges of the tropics, the Andes, the mountains of East Africa, the highlands of Southeast Asia, are among the most species-rich regions on Earth, their biodiversity a cumulative product of millions of years of topographically mediated evolutionary experiment. The mountain as weathermaker extends beyond orographic precipitation into its role as a generator of localized convective weather. On sunny summer afternoons, mountain slopes heated differentially by solar radiation create anabatic winds, upslope flows driven by the buoyancy of warmed air over the sun-facing slopes. These rising air currents carry moisture aloft, cooling it adiabatically until condensation occurs, often producing the characteristic afternoon thunderstorms that climbers in ranges from the Alps to the Andes and Rockies learn to anticipate with respect and, when caught on an exposed ridge, with genuine apprehension. The lightning associated with these convective storms is not merely a statistical hazard. Mountain ridges, composed of often electrically conductive rock and elevated directly into the storm-generating layer of the atmosphere, are struck with frequencies that have generated significant casualties among climbers and, in some ranges, entire communities. Alpine climbing protocols developed in response to this hazard, starting early to reach summits before afternoon convection builds, descending exposed ridges when cloud buildup begins, encode a practical meteorologic. High-altitude astronomy exploits the mountain's dual gift of reduced atmospheric turbulence and reduced atmospheric absorption of electromagnetic radiation. The major observatories of Mauna Kea in Hawaii, Cerro Paranal and Cerro Atacama in Chile, and the Tibetan Plateau in China are all situated at altitudes where the overlying column of atmosphere, and specifically the water vapor within it, which absorbs infrared radiation, is greatly reduced relative to sea level locations. The exceptional seeing conditions at these sites, the stability of the air through which astronomical images must be gathered, arise partly from the altitude itself and partly from the specific meteorological conditions that prevail above the trade wind inversion layer in Hawaii or above the arid desert air in Chile. The concentration of the world's most powerful optical telescopes on a handful of high-altitude mountain peaks has created a paradox of scientific progress. The same peaks regarded as sacred by indigenous communities are simultaneously the sites most sought after for global scientific infrastructure, generating ongoing cultural and legal conflicts about the appropriate uses of high places. The acoustic properties of mountain environments create experiences of sound that flatten description and resist ordinary vocabulary. In deep, narrow alpine valleys, sound reflects from steep walls and returns to the listener with a clarity and multiplicity of echo that transforms a shout or a horn note into something approaching music. The Swiss Alphorn, that impossibly elongated wooden horn whose mournful, resonant tones carry across valleys and seem to condense distance itself into audible form, was developed partly as a long-distance communication instrument in mountain terrain where visual communication was often impossible. Its fundamental note and harmonic overtones are exploited by skilled players to produce melodies entirely from the instrument's natural resonance modes. Mountain silence, conversely, the silence of snowfall, of high windless days above treeline, of glacial cirques sealed from valley sounds, has a quality distinct from any other silence. A presence rather than an absence, as though the mountains themselves are engaged in some form of communication taking place at frequencies below human hearing, a geological conversation conducted across geological time. The specific heat of rock, its capacity to absorb and retain solar energy, makes mountain slopes effective thermal masses that moderate the temperature extremes of surrounding air. Dark-colored rocks, particularly basalts and dark schists, absorb solar radiation with exceptional efficiency, warming to temperatures well above ambient air temperature on sunny days. Climbers resting against sun-warmed south-facing rock faces in otherwise cold conditions exploit this thermal mass effect, using the mountain itself as a radiator. The same thermal mass effect operates at larger scales. Mountain ranges facing equatorward absorb solar energy through summer months and release it gradually through winter, moderating the temperatures of adjacent valleys and lowlands. The Mediterranean climate of certain mountain valleys, warm, frost-moderated winters permitting wine, grape, and olive cultivation at surprisingly high latitudes, is partly a product of this thermal mass effect combined with the cold air drainage patterns that prevent cold air from accumulating in valley bottoms on still, clear nights when radiation cooling would otherwise drive temperatures below freezing. The history of altitude record-breaking in mountaineering traces a fascinating trajectory of technological ambition and physiological experimentation. Early Himalayan expeditions debated vigorously whether the extreme altitudes of the 8000ers could be climbed at all without supplemental oxygen, with eminent physiologists arguing that the human body could not survive aerobic exercise at the partial pressures of oxygen prevailing above approximately 7,600 meters. The debate was resolved empirically. Reinhold Messner and Peter Habeler's oxygen-free ascent of Everest in 1978 demonstrated that human physiology could sustain the effort, though barely and not without significant physiological cost and some irreversible effects. The subsequent history of high-altitude mountaineering has been partly a story of discovering the boundaries of human physiological plasticity, learning, through direct and sometimes fatal experimentation, precisely where the human organism encounters conditions beyond its adaptive capacity. The icefall that descends the upper slopes of many Himalayan peaks, a chaotic tumble of crevasses, seracs, and unstable ice towers created where a glacier flows over a steep underlying rock step, represents some of the most objectively dangerous terrain in mountain environments. The Khumbu icefall below Everest's western comb is the most celebrated example. The icefall through which every route to Everest from the Nepal side must pass is perpetually active, its seracs and towers falling unpredictably as the glacier flows and deforms beneath solar heating and gravitational stress. The icefall doctors, Sherpa climbers who establish and maintain the route through the Khumbu icefall each season, fixing ropes and placing ladders across crevasses, perform work of extraordinary technical difficulty and daily physical danger that receives far less public attention than the summit attempts it enables. The icefall has claimed more lives than any other single section of the Everest route, its hazards immune to skill or acclimatization, responsive only to the timing decisions that determine whether a particular section of glacier moves before or after a climber passes through. The measurement of time in geological terms requires mental tools that are fundamentally different from those applied to human history, yet the rocks of mountain ranges speak, for those trained to read them, with extraordinary temporal specificity. Radiometric dating, the measurement of the ratio of parent-to-daughter isotopes in radioactive decay systems, allows the age of igneous and metamorphic rocks to be determined with remarkable precision. Uranium lead dating of zircon crystals has constrained the timing of Himalayan metamorphism and granite emplacement to within a few million years. Potassium argon dating of volcanic rocks allows the history of volcanic mountain ranges to be traced across millions of years of eruption, dormancy, and renewed activity. Even relative dating, the principle that lower strata are older than upper strata and that cross-cutting features are younger than the rocks they cut, allows a detailed temporal narrative to be constructed from the rock sequence exposed in a mountain cliff face, each layer a chapter in a biography whose total length may span hundreds of millions of years of Earth history. The vertical wilderness imposes its most absolute demands not during the climb but during the descent, a reality that climbers have always known and that statistics grimly confirm. The majority of mountaineering fatalities occur during the descent rather than the ascent. Exhaustion accumulated during the climb, the psychological relief of having reached the summit, hypoxia increasingly affecting judgment, and the technical demands of down-climbing steep terrain, all conspire to make the return to lower altitude more hazardous than the initial upward journey. The mountaineering aphorism, "The summit is optional, the descent is mandatory," encodes this statistical wisdom in memorable form. High-altitude cerebral edema and pulmonary edema, the two most immediately life-threatening altitude illnesses, frequently strike during descent or after extended time at extreme altitude. They're symptoms of severe headache, confusion, loss of coordination, and breathlessness requiring immediate downward movement, which may be precisely what the affected climber is least capable of undertaking without assistance. The mythology of mountains as barriers between the human world and the divine spans cultures from every inhabited continent, expressing an intuition so consistent across independent traditions that it suggests something deep in human cognition about the relationship between height, transcendence, and the sacred. In Hinduism, Mount Meru, a mythological peak at the center of the cosmos, around which all existence revolves, simultaneously reflects the sacred geography of actual Himalayan peaks like Kailash and expresses a cosmological model in which the vertical axis connecting Earth, human realm, and heaven is geometrically embodied in mountain form. In Buddhism, the mandala, that schematic diagram of the cosmos used as a meditation object, is frequently structured around a central peak, Mount Sumeru, that recapitulates the Meru mythology while connecting it to the specific geographical reality of the Himalayan world in which Buddhism emerged. In Christianity, Moses received the law on Sinai, Elijah encountered the divine on Horeb, Jesus was transfigured on an unnamed mountain height. The mountain as the site of revelatory encounter with the transcendent is not incidental but structural to these traditions, a theological architecture built on geological fact. The specific experience of standing on a mountain summit, that singular confluence of physical exhaustion, spatial disorientation, panoramic vision, and atmospheric thinness, has been described in remarkably consistent terms across mountaineering literature from every culture and era. A simultaneous sense of smallness and expansion, of belonging to something vastly larger than the self while simultaneously perceiving the self with unusual clarity. Whether this experience reflects the neurological effects of mild hypoxia acting on specific brain circuits, the psychological processing of an achieved goal after sustained effort, the aesthetic impact of panoramic vision from an elevated vantage point, or something less reducible to mechanism remains genuinely uncertain. What is clear is that the summit experience has, for thousands of climbers across 2 centuries of recorded alpinism, functioned as a threshold, a moment before which the world was one thing and after which it was subtly, permanently different, the mountain having altered the person who climbed it in ways that descending to the valley floor cannot entirely undo. Mountain rivers, those fast, cold, oxygen-rich streams cascading from snowfields and glaciers through gorges and meadows toward the lowland world, are among the most biologically productive aquatic habitats in the world relative to their size, sustaining diverse communities of invertebrates and fish adapted to conditions of high flow velocity, cold temperature, and exceptional water clarity. The bottom-dwelling invertebrates of mountain streams, stoneflies, mayflies, caddisflies, blackflies, have evolved extraordinary specializations for life in fast-flowing cold water, flattened bodies that reduce drag, grappling appendages that grip substrate against current, behavioral aggregations in the most sheltered microhabitats. These invertebrates are the foundation of the food web that supports mountain-adapted fish, brown trout, bull trout, cutthroat trout, and their relatives across mountain ranges worldwide, whose cold water thermal requirements make them acutely sensitive to the temperature increases associated with reduced snowpack, earlier snowmelt, and reduced summer flow that global warming is imposing on mountain river systems across the temperate and boreal world. The salt flats and high-altitude lakes of the Andean Altiplano, that vast, enclosed plateau at 3,600 to 4,000 meters between the eastern and western Cordilleras of the Andes, harbor some of the most chemically extreme and biologically specialized aquatic environments on Earth. Lakes like Laguna Colorada in Bolivia derive their distinctive red-pink color from the dense blooms of halophilic algae and the flamingos that feed on them, filtering brine through specialized lamellate beaks that extract algae and invertebrates from water so saline, alkaline, and mineral-laden that it would be toxic to most organisms. 3 of the world's 6 flamingo species breed on Altiplano salt lakes, the James's flamingo being perhaps the most extreme specialist, nesting at altitudes above 4,500 meters in conditions of intense cold, severe UV radiation, and chemical extremity that would challenge organisms a fraction as physiologically complex. The flamingo's pink coloration derives from carotenoid pigments in the algae they consume, making their color literally a metabolic transformation of their extreme landscape into visible biological form. The mineral wealth of mountain ranges, gold, silver, copper, tin, lead, zinc, and dozens of other economically significant elements concentrated by geological processes in mountain-building environments, has driven human penetration of otherwise barely accessible terrain throughout recorded history. The silver mines of Potosí in the Bolivian Andes, operated from the 16th century onward, were among the most productive in the world and fueled the colonial economy of Spanish America at immense human cost to the indigenous and enslaved African laborers who extracted the ore at altitudes above 4,000 meters under conditions of oxygen deprivation, cold, and extraordinary physical demand. The copper deposits of the Chilean Andes, the gold of the Sierra Nevada, and the tungsten of the Himalayas all represent concentrations of metallic elements created by geological processes, hydrothermal mineralization, magmatic differentiation, metamorphic fluid flow, that occurred hundreds of millions of years before any human beings sought them, their economic significance entirely contingent on the particular historical moment in which human civilization developed the technological capacity to extract and use them. The relationship between mountain ranges and human cultural boundaries is complex and often counterintuitive. While mountains are conventionally regarded as natural barriers that separate cultures and languages, many mountain ranges have historically been corridors as much as barriers, their passes serving as trade routes, migration pathways, and lines of cultural contact that connected rather than divided the communities on either side. The Silk Road moved goods, religions, diseases, technologies, and ideas through the passes of the Pamir and Karakoram ranges. The Alpine passes connected Mediterranean and Northern European civilizations across millennia. The Andean routes linked highland and lowland communities in systems of ecological complementarity that were essential to pre-Columbian subsistence. Mountain communities that controlled critical passes often accumulated wealth and cultural complexity disproportionate to their population size, their geographic position transforming what might otherwise be marginal terrain into nodes of exchange and power within larger regional networks of interaction. The extraordinary biodiversity of the mountains of Ethiopia, particularly the Simien Mountains and the Bale Mountains, harbors several species found nowhere else on Earth, products of the long evolutionary isolation of the Ethiopian highlands from adjacent lowland regions. The Ethiopian wolf, the most endangered carnivore in Africa and the rarest canid on Earth, hunts the Afro-alpine moorlands of the Bale Mountains above 3,000 meters for the high-altitude rodents, particularly the giant mole rat, that dominate the small mammal fauna of these grasslands. The gelada baboon, unique to the Ethiopian highlands, is the only extant species of grass-grazing primate and spends its days methodically harvesting the grasses and herbs of high-altitude meadows, its fingers adapted to plucking individual grass blades with a precision no other non-human primate approaches. The walia ibex, restricted to a small area of the Simien Mountains, survived in the 20th century in numbers so small, fewer than 200 individuals in some estimates, that its continued existence represents one of conservation biology's precarious victories against the combined pressures of habitat loss, hunting, and human encroachment. The science of dendroclimatology, the reconstruction of past climate from the growth rings of ancient trees, has found some of its most valuable research subjects in the gnarled and ancient conifers of high-altitude tree-lean environments. The bristlecone pines of the White Mountains of California, growing at elevations between 3,000 and 3,600 meters in conditions of extreme cold, dry, and nutrient poverty that severely limit their growth but simultaneously restrict the fungal decay that would otherwise destroy old wood, include individual trees whose ages exceed 5,000 years, among the oldest living organisms on Earth. Their annual growth rings, varying in width and density in response to the temperature and moisture conditions of each growing season, encode a climatic record stretching back millennia. Cross-dating the rings of living and dead wood from bristlecone pine populations has allowed the construction of continuous chronologies extending back more than 8,000 years, providing climate scientists with a high-resolution record of temperature and moisture variability that extends deep into prehistory, against which modern instrumental records and computer climate models can be calibrated and validated. The geology of the Scottish Highlands records a mountain-building episode of such antiquity that the mountains themselves have long since been erased by erosion, their former presence indicated only by the extraordinary complexity of metamorphic and igneous rocks that once formed their deep roots. The Caledonian orogeny, which built a mountain chain rivaling the modern Himalayas across what is now Scotland, Scandinavia, and the northeastern coast of North America approximately 400 to 500 million years ago, has left behind a landscape of extraordinary geological diversity. Ancient gneisses among the oldest rocks exposed anywhere in Europe, thrust sheets of once deep metamorphic rocks moved horizontally over ancient basement by the compressional forces of continental collision, and remains of granitic intrusions that once lay far beneath mountain summits. Scotland's present topography, the gentle, rounded hills of the southern uplands, the more rugged Grampians and Cairngorms, is not the Caledonian mountain range but its deeply eroded remnant, a geological scar rather than a mountain system, the ghost of a landscape of a grandeur comparable to anything existing on Earth today. Volcanic mountains, those peaks built by the accumulation of erupted material around a central vent or along a fissure, display a diversity of form, activity, and geological character that distinguishes them fundamentally from fold and thrust mountains despite their sometimes similar surface appearance. The shield volcanoes of Hawaii, built from repeated eruptions of fluid basaltic lava that spread far from the vent before solidifying, produce broad, gently sloping edifices that rise from the ocean floor to immense heights but present a landscape of subdued relief rather than the dramatic peaks of stratovolcanoes. The stratovolcanoes of the Circum-Pacific Ring of Fire, Fuji, Rainier, Hood, Shasta, Popocatépetl, Cotopaxi, Villarrica, are built of alternating layers of lava flows and pyroclastic deposits, their steep conical profiles reflecting the higher viscosity of their silica-rich magmas. These stratovolcanoes are the most explosively hazardous of volcanic types. Their viscous magmas trap gas, building pressure until catastrophic explosive eruption releases it. The 1980 eruption of Mount St. Helens, which removed the entire north flank of the mountain and reduced its summit by nearly 400 meters in a lateral blast heard from hundreds of kilometers away, remains the most destructive volcanic event in modern American history. The fumaroles, hot springs, and hydrothermal features associated with volcanically active mountain systems support microbial communities of extraordinary metabolic diversity, organisms that thrive in conditions of near-boiling temperature, extreme acidity, and chemical environments dominated by sulfur, arsenic, and other compounds toxic to most life. The study of these hyperthermophilic archaea and bacteria, organisms whose optimal growth temperatures may exceed 80 or even 100 degrees Celsius, has transformed understanding of the physical limits of life and the evolutionary history of metabolism on Earth. Many of the fundamental metabolic pathways shared by all living organisms on Earth were likely developed in environments resembling the hydrothermal systems of early Earth, making volcanic mountain systems not merely geological curiosities but potential windows into the conditions in which life originated approximately 3.8 billion years ago. The enzymes of thermophilic bacteria, stable at temperatures that would denature most proteins, have found significant practical applications in biotechnology, most notably in the polymerase chain reaction techniques that underlie modern molecular biology and forensic DNA analysis. The Andes Mountains of South America constitute not merely the world's longest continental mountain chain but one of the most significant drivers of evolution and biological diversification on the planet. The progressive uplift of the Andes from relatively low hills approximately 20 million years ago to their current heights over the subsequent geological epochs drove the diversification of South American flora and fauna by creating a continuously enlarging heterogeneous landscape across which new species could arise in isolation. The extraordinary diversity of Andean birds, particularly hummingbirds, which have radiated into more than 130 high Andean species adapted to specific elevation zones and flower types, represents one of the most spectacular evolutionary radiations in vertebrate history. The Andes also drove the diversification of Andean plants, particularly the genus Lupinus, which has diversified into more than 80 Andean species as it colonized the diverse ecological conditions created by the mountain's geological uplift, providing botanists with a near-perfect natural experiment in how topographic complexity promotes speciation. The Karakoram Range, that collection of extreme peaks and glaciers in the border region of Pakistan, China, and India, contains the greatest concentration of high mountains outside the Himalayas, more than 60 summits exceeding 7,000 meters and 4 exceeding 8,000 meters in an area small enough to traverse on foot in a matter of weeks. The Karakoram is also home to the largest glaciers outside the polar ice caps, the Siachen, Biafo, Baltoro, and Hispar glaciers, massive rivers of ice whose total area exceeds 15,000 square kilometers. Unlike the retreating glaciers of most mountain ranges, certain Karakoram glaciers show anomalous surge behavior and some evidence of recent advance or stability rather than consistent retreat, a phenomenon not fully understood but possibly related to the unique topographic configuration of the range and the moisture dynamics of its extreme altitude. The political geography of the Karakoram is as complex as its physical geography. The Siachen Glacier, the world's highest battlefield, has been disputed between India and Pakistan since 1984, with military outposts maintained at altitudes above 6,000 meters in conditions that constitute a severe physiological challenge even without the additional hazard of armed conflict. The specific light quality of mountain environments, particularly the clarity and intensity of illumination at high altitude and the extraordinary colors of sunrise and sunset as seen from elevated vantage points, has exerted a distinctive influence on the art produced by cultures with deep mountain connections. The Japanese woodblock print tradition, the Swiss Romantic painting tradition, the American Hudson River School's responses to the Appalachians and Adirondacks, and the luminous high-altitude photography of Ansel Adams in the Sierra Nevada all share an aesthetic preoccupation with the particular qualities of mountain light: its clarity, its directionality, its capacity to transform familiar rock and snow into something approaching the supernatural. Turner's late paintings of alpine storms capture the sublime dissolution of form in atmospheric light with an expressionistic intensity that anticipates abstraction by half a century. The mountain light that appears in so much of this art is not merely a technical condition but a cultural symbol. The light above the clouds, above the valley fog, above the compromised air of inhabited lowlands, has come to signify clarity of perception, purity of vision, and access to truth that ordinary life occludes. The concept of wilderness, that idealized space of nature untouched by human intervention, is perhaps nowhere more deeply problematized than in mountain environments. Every mountain range in the inhabited world bears the marks of human presence extending back millennia: the terraced agriculture of Andean and Himalayan slopes, the pastures created by millennia of alpine grazing, the managed forests of European mountain ranges, the indigenous fire practices that shaped the vegetation of North American mountain ranges, the archaeological sites of high-altitude hunting and ritual activity found from the Arctic to the tropics. The wild landscape that modern visitors experience as pristine is frequently the product of long human management, its present ecological composition inseparable from centuries or millennia of human influence. This recognition does not diminish the value of mountain ecosystems. It enriches our understanding of them, placing them within a history of human-nature interaction that is far more complex, more nuanced, and more reciprocal than the simple opposition of human civilization and wild nature allows. The future of mountain glaciers, those frozen reservoirs upon whose seasonal melt hundreds of millions of people partially depend for drinking water, irrigation, and hydroelectric power, constitutes one of the most consequential environmental stories of the 21st century. Global analyses indicate that if current trajectories of greenhouse gas emissions continue, the majority of the world's mountain glaciers will lose more than half their mass by 2100, with smaller glaciers disappearing entirely. The immediate consequence of accelerating melt is, paradoxically, a temporary increase in runoff as glaciers contribute more meltwater than they accumulate in snowfall. A brief hydrological dividend followed by the permanent reduction in summer flows that glacial loss entails. The communities most vulnerable to this transformation are typically those that have depended on glacier-fed rivers for generations, their agricultural calendars, urban water systems, and cultural identities built around a hydrological regime that is now undergoing rapid fundamental change. No purely technological solution, water storage, desalination, transfer infrastructure, can fully substitute for the patient, centuries-long work of glacial water storage that atmospheric warming is now undoing. The atmosphere of Venus, Mars, and other terrestrial planets in our solar system has been shaped partly by the presence or absence of mountain-building processes. On Earth, plate tectonics and the resulting mountain building play a crucial role in the long-term carbon cycle. Silicate rocks exposed by erosion of mountain ranges react with atmospheric carbon dioxide in chemical weathering reactions that sequester carbon in ocean sediments, drawing down atmospheric CO2 over geological timescales. This silicate weathering feedback is one of the key mechanisms that has maintained Earth's climate within habitable bounds across billions of years, despite a sun that has grown approximately 30% brighter over that period. The rates of this weathering are proportional to the height and extent of mountain ranges. Periods of active mountain building tend toward cooling, periods of orogenic quiescence toward warming. The mountains are thus not merely passive features of the planetary surface but active regulators of the atmospheric composition and climate that make Earth habitable, geological architects of the conditions within which all life on Earth, including ourselves, has evolved. The mountains have been, across the full span of human history, simultaneously obstacles and sanctuaries, challenges and consolations, places of death and places of renewal. They have shaped the climates that determined which civilizations rose and fell in the valleys below them. They have stored the water that made agriculture possible across half the inhabited world. They have sheltered genetic diversity of plants, animals, and human cultures in their isolated valleys during the planetary catastrophes that periodically simplified the biosphere. They have provided humanity with its most potent metaphors for aspiration, transcendence, and the relationship between effort and meaning. And they have humbled every civilization that has approached them with the assumption that their scale, their age, and their indifference to human ambition could be mastered rather than merely, humbly, incompletely understood. The mountain does not care whether you reach its summit. It was here before the word for summit existed. It will be here long after the last human word has been spoken, still ascending by its 5 millimeters each year, still surrendering its summit to the sky. We descend now, as all mountain journeys must end, back through the layers of compressed time, past the tree line where gnarled conifers resume their centuries-long conversation with the wind, through the meadows where glacier-carved valleys hold their blue lakes like mirrors offered to the sky, down to the valley floors where rivers carry the mountain's own substance seaward in dissolution. The mountains we leave behind are not the same mountains we approached. Knowledge changes landscapes as surely as glaciation does, replacing simple mass with understood complexity, substituting the known for the merely perceived. And yet knowledge does not exhaust the mountain. It deepens the mystery rather than resolving it. To understand how the Himalayas formed is not to explain why standing at their base induces something approaching reverence. An emotion that has no geological name but that every person who has ever genuinely faced a great mountain has felt, as though the body, older than consciousness, remembers something about the relationship between living things and stone that the mind has not yet found the language to articulate. These 100 truths about mountains are not, in any ultimate sense, the truth about mountains. They are 100 windows opened in a wall of stone, each revealing a different angle of light, a different depth of shadow, a different portion of what lies within. The geology continues below the basement rocks into the mantle and toward the core. The biology extends below the visible plants into the microbial films coating mineral grains and dissolving stone into soil. The history extends backward before the first human eye turned upward toward a summit into the pre-biological eons when mountains rose and fell without witness. And the meaning, that most human of all mountain questions, extends in every direction at once. Backward into myth and forward into whatever relationship our civilization will negotiate with these irreplaceable, irreducible presences as the climate we have altered reshapes the conditions that have defined them since before the first of our ancestors looked upward, saw a summit vanishing into cloud, and felt, without knowing why, the pull of the vertical wilderness calling them toward a height they could not yet name. The phenomenon of mountain mirages, those optical distortions that bend, duplicate, and invert distant peaks along the horizon, arises from the layering of air masses of different temperatures and densities in the atmosphere above high terrain. When a layer of warm air sits above a layer of cold air, as frequently occurs in calm mountain valleys at dawn and dusk, light traveling through the boundary between these layers is refracted, bent along curved paths that carry visual information from beyond the geometric horizon or that duplicate distant summits into ghostly floating replicas above their actual positions. The Fata Morgana mirage, named for the Arthurian sorceress Morgan Le Fay, whose enchantments were understood to create illusory castles above the sea, produces stacked, vertically compressed images of distant mountains that appear as elaborate architectural structures suspended impossibly in midair. Alpine communities across Europe and Asia developed rich folkloric traditions around these optical phenomena, interpreting the doubled and inverted mountains as portals, omens, or manifestations of the mountain's spiritual double, its soul, ascending from its physical body toward the sky, momentarily made visible to those patient and attentive enough to witness the transformation. The biological phenomenon known as cryptobiosis, a state of suspended animation in which metabolic activity effectively ceases in response to environmental extremity, reaches perhaps its most dramatic expression in the tardigrades, microscopic eight-legged animals found across mountain environments from temperate meadows to the highest accessible rock surfaces on Earth. When confronted with desiccation, freezing, or radiation levels lethal to virtually all other organisms, tardigrades withdraw their legs, expel nearly all body water, and enter a desiccated state called a ton in which they can survive conditions of extraordinary severity, temperatures approaching absolute zero, pressures hundreds of times atmospheric, radiation doses thousands of times the lethal human threshold, and the near-complete vacuum of open space. Tardigrades have been found in the sediments of high Himalayan lakes, in the mosses of Antarctic mountain ridges, and in the meltwater films of alpine glaciers, ecosystems at the extreme margins of biological possibility. Their survival strategies challenge every assumption about the boundaries of life, suggesting that the vertical wilderness harbors organisms whose biological resilience exceeds anything our intuitions about fragility and survival would predict, pushing the concept of habitability into domains previously considered purely physical. The science of mountain meteorology has advanced dramatically in the satellite era, as instruments orbiting hundreds of kilometers above Earth's surface now provide continuous, high-resolution observations of cloud formation, precipitation, wind patterns, and temperature across terrain that was previously accessible only to scattered surface weather stations. Satellite-based radar can now measure precipitation falling over the most remote Himalayan and Andean peaks with precision unavailable to any ground-based network, revealing the spatial complexity of orographic precipitation at scales too fine for earlier instruments to resolve. Geostationary satellites monitor the development of convective storms over mountain ranges in real time, providing data that feeds into weather forecast models with life-saving implications for mountaineers, pilots, and the mountain communities whose vulnerability to flash floods and avalanches depends on accurate advance warning. Yet the fundamental challenge of mountain meteorology remains. The complexity of airflow over and around mountain topography creates atmospheric behavior of such chaotic sensitivity that forecast accuracy degrades rapidly beyond roughly 3 days, leaving the vertical wilderness in possession of a meteorological unpredictability that no satellite, however sophisticated, can fully resolve into reliable prediction at the local scales that matter most to human safety. The relationship between mountain ecosystems and carbon storage has emerged as one of the more consequential questions in contemporary environmental science, as researchers work to quantify the contribution of high-altitude soils, vegetation, and permafrost to the global carbon cycle. Mountain soils, though often thin and poorly developed, can accumulate significant quantities of organic carbon in cold conditions where the low temperatures that limit plant growth simultaneously limit microbial decomposition of dead organic matter. Alpine peatlands and bogs, where waterlogged conditions further restrict decomposition, can contain carbon stocks accumulated over thousands of years since the last glaciation. As temperatures rise and permafrost thaws, this stored carbon becomes vulnerable to decomposition, releasing carbon dioxide and methane into the atmosphere and potentially creating positive feedback loops that accelerate further warming. The Tibetan Plateau alone contains permafrost underlying an area of approximately 1.3 million square kilometers, with soil carbon stores whose potential release under continued warming represents a significant, if difficult to precisely quantify, contribution to future atmospheric greenhouse gas concentrations. Understanding and monitoring these mountain carbon reservoirs has thus become a priority in global climate science, their remote inaccessibility complicating the observational programs required to track their changing state. The architectural traditions developed by mountain cultures across the world share recurring structural principles that reflect the specific demands and available materials of high-altitude environments, producing a vernacular building heritage of extraordinary regional diversity and functional elegance. The stone towers of the Caucasus, those slender, multi-story defensive structures rising from Georgian and Chechen village complexes, were built without mortar, their precisely fitted dry stone construction exploiting the tensile properties of local schist and limestone to achieve heights of 20 meters or more in seismically active terrain. The Tibetan dzong, that massive, fortress monastery building type whose whitewashed walls and tapering buttresses dominate the valleys of Bhutan and Tibet, was engineered to resist both military assault and the thermal extremes of high-altitude continental climate, its massive walls providing thermal mass, its south-facing orientation maximizing passive solar gain during the long, intensely cold winters. The terraced villages of Yemen's Haraz Mountains, the cliff dwellings of the American Southwest's Canyon Country, and the stone-built hamlets of the Scottish Highlands all testify to the same fundamental principle. In mountain environments, building in harmony with the geological and climatic realities of the vertical world is not merely aesthetically appropriate but existentially necessary. The experience of solitude in mountain environments, that particular quality of aloneness achievable in high places that differs qualitatively from solitude experienced in urban or lowland settings, has been a recurring preoccupation of mountain writers, philosophers, and spiritual practitioners across cultures and centuries. The solitude of the high places is not merely the absence of other people but the presence of a scale of existence against which human individuality becomes simultaneously less significant and more clearly defined. Friedrich Nietzsche wrote portions of Thus Spoke Zarathustra while walking mountain paths above Sils Maria in the Swiss Engadine, crediting the altitude and solitude with releasing a creative and philosophical intensity unavailable to him at lower elevations. The desert fathers of early Christianity sought mountain solitude in the ranges of Egypt and Syria as the necessary condition for the contemplative life. Zen mountain traditions in China and Japan treated high-altitude hermitage as the appropriate environment for advanced meditation practice, the mountain's combination of physical austerity and panoramic clarity providing what the crowded valley could not: a silence spacious enough to hear what ordinarily goes unheard, a perspective elevated enough to see what proximity to the ordinary world perpetually obscures from the spiritually attentive mind. The glaciological concept of mass balance, the relationship between the snow and ice a glacier gains through precipitation and the snow and ice it loses through melting, evaporation, and calving, provides the most direct and sensitive measure of how individual glaciers respond to climate variability. A glacier with positive mass balance is growing, one with negative mass balance is shrinking. The World Glacier Monitoring Service has tracked mass balance measurements for reference glaciers across mountain ranges worldwide since the mid-20th century, assembling a global dataset that now constitutes one of the most compelling bodies of evidence for climate change available to science. The record shows that the overwhelming majority of monitored glaciers have experienced negative mass balance in recent decades, with the rate of mass loss accelerating markedly since the 1980s. Particularly striking are the losses documented in the tropical Andes, the East African mountains, and the European Alps, where small glaciers are disappearing entirely within observational timescales, not shrinking gradually towards some new equilibrium but vanishing from landscapes where they have been present since before the earliest human records of the terrain. Each disappearing glacier represents not merely a loss of ice but the erasure of a hydrological and cultural landmark whose absence will reshape the landscapes, economies, and identities of the communities that have lived in its presence for generations. The deep time perspective that mountains offer, their capacity to compress billions of years of planetary history into a cliff face readable to those with geological training, has profound philosophical implications that extend well beyond the technical domain of earth science. When James Hutton, the Scottish geologist who is widely regarded as the founder of modern geology, observed the unconformity at Siccar Point on the Scottish coast in 1788, where near-horizontal Devonian red sandstone rests upon the vertical edges of much older Silurian greywacke, representing a gap of hundreds of millions of years, he is reported to have declared that he found no vestige of a beginning, no prospect of an end. This recognition of deep time, of Earth history operating on scales so vast that human intuition cannot directly apprehend them, was one of the most intellectually revolutionary insights of the Enlightenment, undermining biblical chronology and ultimately helping to create the intellectual space within which Darwin's theory of evolution by natural selection could be formulated and accepted. The mountains were the text in which this revolutionary idea was first clearly read, their layered rocks the evidence that time itself was a dimension of a different order than anything human civilization had previously imagined. The sounds that mountains make, independent of the wind, the water, and the wildlife that inhabit them, have been documented and studied with increasing scientific rigor as seismological instrumentation has become sufficiently sensitive to detect the subtle acoustic signatures of geological processes operating at the surface. Glaciers groan and crack as thermal expansion and contraction stress their ice, producing sounds that carry through the ice itself as well as through the rock beneath. Rockfall generates characteristic seismic signatures detectable at stations many kilometers distant, allowing automated monitoring systems to identify and locate mass movements in real time. The low-frequency rumble of debris flows, those fast-moving slurries of water, rock, and sediment that rush down mountain gullies during intense rainfall, can be detected and characterized by seismic stations, providing warning times of minutes to tens of minutes that can be the difference between successful evacuation and catastrophe. Even the slow, inexorable flow of glaciers generates detectable seismic tremor, a kind of continuous murmur emanating from the bed of the ice where it slides over rock, a geological heartbeat that instruments can measure and that, if we were to translate it into the range of human hearing, would sound something like the sustained, barely audible note of a string instrument bowed with extraordinary lightness and infinite patience. Mountains, in their totality, are the planet's most complete autobiography, geological, biological, atmospheric, and human, written in a language of stone, ice, altitude, and time that rewards learning with an ever-deepening appreciation of complexity. They formed the climates that made civilization possible. They stored the water that fed the first irrigated fields. They sheltered the genetic diversity that allowed life to survive the great extinctions. They inspired the myths that gave early cultures their cosmological frameworks. They challenged the explorers whose expeditions extended the limits of human geographical knowledge. They taught the scientists whose observations of rock, ice, and biology transformed our understanding of how the Earth works and how life adapts to its most demanding conditions. And they continue, in the 21st century, to serve as both barometers and bellwethers of the planetary changes our civilization has set in motion, their retreating glaciers, shifting treelines, and warming permafrost among the clearest signals available to science that the atmospheric experiment of industrial civilization is altering the fundamental physical conditions of the world we inherited. To understand mountains is to understand Earth. And to love them, as every person who has genuinely encountered their silence, their scale, and their indifference to human urgency eventually does, is to love the planet that made them, and that they, in turn, continue quietly to make. The phenomenon of mountain mirages, those optical distortions that bend, duplicate, and invert distant peaks along the horizon, arises from the layering of air masses of different temperatures and densities in the atmosphere above high terrain. When a layer of warm air sits above a layer of cold air, as frequently occurs in calm mountain valleys at dawn and dusk, light traveling through the boundary between these layers is refracted, bent along curved paths that carry visual information from beyond the geometric horizon or that duplicate distant summits into ghostly floating replicas above their actual positions. The Fata Morgana mirage, named for the Arthurian sorceress Morgan Le Fay, whose enchantments were understood to create illusory castles above the sea, produces stacked, vertically compressed images of distant mountains that appear as elaborate architectural structures suspended impossibly in midair. Alpine communities across Europe and Asia developed rich folkloric traditions around these optical phenomena, interpreting the doubled and inverted mountains as portals, omens, or manifestations of the mountain's spiritual double, its soul, ascending from its physical body toward the sky, momentarily made visible to those patient and attentive enough to witness the transformation. The biological phenomenon known as cryptobiosis, a state of suspended animation in which metabolic activity effectively ceases in response to environmental extremity, reaches perhaps its most dramatic expression in the tardigrades, microscopic eight-legged animals found across mountain environments from temperate meadows to the highest accessible rock surfaces on Earth. When confronted with desiccation, freezing, or radiation levels lethal to virtually all other organisms, tardigrades withdraw their legs, expel nearly all body water, and enter a desiccated state called a ton in which they can survive conditions of extraordinary severity, temperatures approaching absolute zero, pressures hundreds of times atmospheric, radiation doses thousands of times the lethal human threshold, and the near-complete vacuum of open space. Tardigrades have been found in the sediments of high Himalayan lakes, in the mosses of Antarctic mountain ridges, and in the meltwater films of alpine glaciers, ecosystems at the extreme margins of biological possibility. Their survival strategies challenge every assumption about the boundaries of life, suggesting that the vertical wilderness harbors organisms whose biological resilience exceeds anything our intuitions about fragility and survival would predict, pushing the concept of habitability into domains previously considered purely physical. The science of mountain meteorology has advanced dramatically in the satellite era, as instruments orbiting hundreds of kilometers above Earth's surface now provide continuous, high-resolution observations of cloud formation, precipitation, wind patterns, and temperature across terrain that was previously accessible only to scattered surface weather stations. Satellite-based radar can now measure precipitation falling over the most remote Himalayan and Andean peaks with precision unavailable to any ground-based network, revealing the spatial complexity of orographic precipitation at scales too fine for earlier instruments to resolve. Geostationary satellites monitor the development of convective storms over mountain ranges in real time, providing data that feeds into weather forecast models with life-saving implications for mountaineers, pilots, and the mountain communities whose vulnerability to flash floods and avalanches depends on accurate advance warning. Yet the fundamental challenge of mountain meteorology remains. The complexity of airflow over and around mountain topography creates atmospheric behavior of such chaotic sensitivity that forecast accuracy degrades rapidly beyond roughly 3 days, leaving the vertical wilderness in possession of a meteorological unpredictability that no satellite, however sophisticated, can fully resolve into reliable prediction at the local scales that matter most to human safety. The relationship between mountain ecosystems and carbon storage has emerged as one of the more consequential questions in contemporary environmental science, as researchers work to quantify the contribution of high-altitude soils, vegetation, and permafrost to the global carbon cycle. Mountain soils, though often thin and poorly developed, can accumulate significant quantities of organic carbon in cold conditions where the low temperatures that limit plant growth simultaneously limit microbial decomposition of dead organic matter. Alpine peatlands and bogs, where waterlogged conditions further restrict decomposition, can contain carbon stocks accumulated over thousands of years since the last glaciation. As temperatures rise and permafrost thaws, this stored carbon becomes vulnerable to decomposition, releasing carbon dioxide and methane into the atmosphere and potentially creating positive feedback loops that accelerate further warming. The Tibetan Plateau alone contains permafrost underlying an area of approximately 1.3 million square kilometers, with soil carbon stores whose potential release under continued warming represents a significant, if difficult to precisely quantify, contribution to future atmospheric greenhouse gas concentrations. Understanding and monitoring these mountain carbon reservoirs has thus become a priority in global climate science, their remote inaccessibility complicating the observational programs required to track their changing state. The architectural traditions developed by mountain cultures across the world share recurring structural principles that reflect the specific demands and available materials of high-altitude environments, producing a vernacular building heritage of extraordinary regional diversity and functional elegance. The stone towers of the Caucasus, those slender, multi-story defensive structures rising from Georgian and Chechen village complexes, were built without mortar, their precisely fitted dry stone construction exploiting the tensile properties of local schist and limestone to achieve heights of 20 meters or more in seismically active terrain. The Tibetan dzong, that massive, fortress monastery building type whose whitewashed walls and tapering buttresses dominate the valleys of Bhutan and Tibet, was engineered to resist both military assault and the thermal extremes of high-altitude continental climate, its massive walls providing thermal mass, its south-facing orientation maximizing passive solar gain during the long, intensely cold winters. The terraced villages of Yemen's Haraz Mountains, the cliff dwellings of the American Southwest's Canyon Country, and the stone-built hamlets of the Scottish Highlands all testify to the same fundamental principle. In mountain environments, building in harmony with the geological and climatic realities of the vertical world is not merely aesthetically appropriate but existentially necessary. The Andes Mountains of South America constitute not merely the world's longest continental mountain chain but one of the most significant drivers of evolution and biological diversification on the planet. The progressive uplift of the Andes from relatively low hills approximately 20 million years ago to their current heights over the subsequent geological epochs drove the diversification of South American flora and fauna by creating a continuously enlarging heterogeneous landscape across which new species could arise in isolation. The extraordinary diversity of Andean birds, particularly hummingbirds, which have radiated into more than 130 high-Andean species adapted to specific elevation zones and flower types, represents one of the most spectacular evolutionary radiations in vertebrate history. The Andes also drove the diversification of Andean plants, particularly the genus Lupinus, which has diversified into more than 80 Andean species as it colonized the diverse ecological conditions created by the mountain's geological uplift, providing botanists with a near-perfect natural experiment in how topographic complexity promotes speciation. The Karakoram Range, that collection of extreme peaks and glaciers in the border region of Pakistan, China, and India, contains the greatest concentration of high mountains outside the Himalayas, more than 60 summits exceeding 7,000 meters and 4 exceeding 8,000 meters in an area small enough to traverse on foot in a matter of weeks. The Karakoram is also home to the largest glaciers outside the polar ice caps, the Siachen, Biafo, Baltoro, and Hispar glaciers, massive rivers of ice whose total area exceeds 15,000 square kilometers. Unlike the retreating glaciers of most mountain ranges, certain Karakoram glaciers show anomalous surge behavior and some evidence of recent advance or stability rather than consistent retreat, a phenomenon not fully understood but possibly related to the unique topographic configuration of the range and the moisture dynamics of its extreme altitude. The political geography of the Karakoram is as complex as its physical geography. The Siachen Glacier, the world's highest battlefield, has been disputed between India and Pakistan since 1984, with military outposts maintained at altitudes above 6,000 meters in conditions that constitute a severe physiological challenge even without the additional hazard of armed conflict. The specific light quality of mountain environments, particularly the clarity and intensity of illumination at high altitude and the extraordinary colors of sunrise and sunset as seen from elevated vantage points, has exerted a distinctive influence on the art produced by cultures with deep mountain connections. The Japanese woodblock print tradition, the Swiss Romantic painting tradition, the American Hudson River School's responses to the Appalachians and Adirondacks, and the luminous high-altitude photography of Ansel Adams in the Sierra Nevada all share an aesthetic preoccupation with the particular qualities of mountain light: its clarity, its directionality, its capacity to transform familiar rock and snow into something approaching the supernatural. Turner's late paintings of alpine storms capture the sublime dissolution of form in atmospheric light with an expressionistic intensity that anticipates abstraction by half a century. The mountain light that appears in so much of this art is not merely a technical condition but a cultural symbol. The light above the clouds, above the valley fog, above the compromised air of inhabited lowlands, has come to signify clarity of perception, purity of vision, and access to truth that ordinary life occludes. The concept of wilderness, that idealized space of nature untouched by human intervention, is perhaps nowhere more deeply problematized than in mountain environments. Every mountain range in the inhabited world bears the marks of human presence extending back millennia: the terraced agriculture of Andean and Himalayan slopes, the pastures created by millennia of alpine grazing, the managed forests of European mountain ranges, the indigenous fire practices that shaped the vegetation of North American mountain ranges, the archaeological sites of high-altitude hunting and ritual activity found from the Arctic to the tropics. The wild landscape that modern visitors experience as pristine is frequently the product of long human management, its present ecological composition inseparable from centuries or millennia of human influence. This recognition does not diminish the value of mountain ecosystems. It enriches our understanding of them, placing them within a history of human-nature interaction that is far more complex, more nuanced, and more reciprocal than the simple opposition of human civilization and wild nature allows. The future of mountain glaciers, those frozen reservoirs upon whose seasonal melt hundreds of millions of people partially depend for drinking water, irrigation, and hydroelectric power, constitutes one of the most consequential environmental stories of the 21st century. Global analyses indicate that if current trajectories of greenhouse gas emissions continue, the majority of the world's mountain glaciers will lose more than half their mass by 2100, with smaller glaciers disappearing entirely. The immediate consequence of accelerating melt is, paradoxically, a temporary increase in runoff as glaciers contribute more meltwater than they accumulate in snowfall, a brief hydrological dividend followed by the permanent reduction in summer flows that glacial loss entails. The communities most vulnerable to this transformation are typically those that have depended on glacier-fed rivers for generations, their agricultural calendars, urban water systems, and cultural identities built around a hydrological regime that is now undergoing rapid fundamental change. No purely technological solution, water storage, desalination, transfer infrastructure, can fully substitute for the patient, centuries-long work of glacial water storage that atmospheric warming is now undoing.